Hello everyone, this is Pablo Barrachina, Industrial Engineer and Project Manager at MIW Energia, one of the members of the Greenfield Consortium. I'm going to present a lecture talking about one of the main renewable energy sources, photovoltaics. I will start with a short introduction about the clean energy package in Europe and the importance of the PV energy. Then, I will explain how the solar energy works and the different PV cells. After that, I will continue with the PV panels and PV systems. And finally, I will finish with the current situation of the PV energy in the world and in Europe. First, I will start with the clean energy package, approved by the European Commission that has set the following goals for 2030. A 40% reduction in greenhouse gas emissions, a 32% share of renewable energy end use, and a 32.5% improvement in energy efficiency. In September of 2020, the European Commission proposed to increase these levels, what is called the Clean Energy Package 2.0. Mainly, it raises the reduction to obtain at least a 55% reduction in greenhouse gas emissions. That will suppose to have around 38 or 40% share of renewable energy end use. So, what the PV energy will look if we achieve these objectives? By 2050, it is expected that the PV energy will be the prime energy source in Europe. Also, the solar roof will help to reduce European building stock emissions by 60% in 2030. Currently, they produce 36% of the emissions in Europe. And despite the effect of COVID-19, solar installation grew an 11% during 2020. Now, let's talk about how the solar energy works and the solar cells. First, I will introduce the photovoltaic effect. It is the effect due to which light energy is converted to electric energy in semiconductor material. This converts light energy to electricity without intermediate process. It was first observed in 1839 by Edmond Becquerel. The PV solar cell is a PN junction diode with different layers. First, the N-type semiconductor layer that is doped with donor impurities and excess of electrons. Also, the P-type semiconductor layer doped with acceptor impurities, excess of holes or protons. Between them, it is the PN junction layer. It's the depletion zone. Also, it has electrodes, the top electrode that do not subtract the light and the bottom electrode. And all of this is encapsulated in a glass. So, how does it work? When light reaches the PN junction, the light photons can easily enter in the junction. The light energy, in the form of photons, supplies sufficient energy to the junctions to create a number of electron-hole pairs. The incident light breaks the thermal equilibrium condition of the junction. The free electrons in the depletion region can quickly come to the N-type side of the junction. Similarly, the holes in the depletion can quickly come to the P-type side of the junction. Once the newly created free electrons come to the N-type side, they cannot further cross the junction because of the barrier potential of the junctions. Similarly, the newly created holes, once come to the P-type side, cannot further cross the junction because of the same barrier of the junction. As the concentration of the electrons becomes higher in the N-type side of the junction, and the concentration of holes becomes more in the P-type side of the junction, the PN junction will behave like a small battery cell. A voltage is set up which is known as photovoltaic. If we connect a small load across the junction, there will be a tiny current flowing through it. Now let's see the characteristics curve of a solar cell. The curve in red shows the voltage current. The horizontal axis represents the working cell voltage, and the vertical axis the current, while the curve in blue shows the power for a cell working at a known temperature and radiation. These two curves show how the energy is produced by a cell or photovoltaic module at a point called operation point in any part of the IV curve. The criteria used to select materials for the solar cells are the following ones: a high optical absorption, a high electrical conductivity, it must be available in abundance, and the band gap must be from 1 electron volt to 1.8 electron volt. The materials most commonly used are silicon, gallium arsenide, cadmium telluride, and copper indium selenide. Now let's talk about the PV module. A single solar cell cannot provide required useful output, so to increase output power level of a PV system, it is required to connect a number of such PV solar cells. A solar module is normally a series-connected, sufficient number of solar cells to provide the required standard output voltage and power. One solar module can be rated from 3 watts up to 500 watts. The output power depends upon some conditions such as ambient temperature and intensity of light radiation. The nominal power of a solar module is given at what is called the standard test condition. That means 25 degrees Celsius and 1000 watts per square meter of light radiation. Each panel has 3 main parameters: the short circuit current, the open circuit voltage, and the maximum power point at the standard test condition. Another 2 parameters to measure the quality of the modules are the fill factors, is the relation between the maximum power and the multiplication of the short circuit current and the open circuit current, and finally the efficiency, that depends mainly of the technology. In this slide we can see how the curve varies changing the ambient temperature, which is better with less temperature, and with the light irradiance. Of course, the more irradiance, the better. Now let's take a look at the different technologies. The ones based on silicon or first generation, the crystalline silicon, monocrystalline with an efficiency of 24.4%, and the multicrystalline with an efficiency of 20.4%. Then the so-called thin film technologies, or the second generation, such as cadmium telluride, copper indium gallium selenide, and the amorphous silicon. Then the third generation, such as organic cells with an efficiency of 15.2%, or the perovskite with an efficiency of 25%. Finally, we got the multi-junction solar cells with the best efficiency tested in the labs so far, with an efficiency that goes from 35 up to 47%. Still, the most common ones are still the first generation crystalline silicon. Here you can see the production by technology. As you can see, the multi-silicon or the monosilicon are by far the most commonly produced. And during the last year, the monosilicon has increased and has regained the first place in the production. If we take a look at the market share of the thin film technology, we can see that the most commonly produced are the cadmium telluride, then the copper indium gallium selenide, and finally the amorphous. This technology, the amorphous, is very cheap, but the efficiency is quite low compared with the others. Now let's talk about the PV systems. There are 2 types of PV system according to the connection to the grid: the standalone solar electrical system off grid and the grid connected PV systems. The standalone solar electrical system of grid. The main uses are to electrify isolated buildings, for public lighting, to power water pumps, for IT systems, and for road traffic signaling. The main components of a standalone solar electrical system are the solar panels, common to all the solar systems, the charge controller that regulate and control the output from the solar array. That's optional, but usually they have batteries that allows to accumulate energy for the nighttime or when the sun doesn't produce enough energy. And in case of if in the system there are AC loads, an inverter that convert the DC current into AC current. Now let's talk about the grid-connected electrical system. The main uses are for PV solar farms and for PV buildings, self-consumption on a grid-connected buildings. The main components are the solar panels, the inverter, and the electricity meter. This system could have also batteries. So in this case, we will have the charge controller in order to regulate the power that goes to the grid or to the loads or to the battery. The battery itself and also the inverter and the electricity meter. Now we will briefly see what are the steps to calculate a standalone installation. First, we will do an estimation of the consumption. We'll take into account all the loads, the domestic appliances, the lighting, the computer, the HVAC system. Second, we will calculate the power capacity of the PV generator. For that, we will apply a security factor and it depends on the location. Third, we will calculate the battery capacity. In that case, we also apply a security factor. That is the number of days using just the battery. Finally, we select the equipment, the number of PV modules and batteries, and after that, the controller and the inverter. For PV solar farms, we have a completely different approach. In this case, what we look at is the available area to install the PV solar farm, the available power capacity in the distribution grid, and finally, the available investments. In order to increase efficiency, usually the PV panels have a solar tracker, a single axis or dual axis, although usually it's more common to have only single axis because the increase in efficiency doesn't compensate the increase in cost. Now, let's talk about the PV installations for self-consumption. The first thing is to obtain the average demand curve of the building. Then, compare the production versus the demand daily to select the power. There's a balance between the total power and self-consumption ratio. The more power, of course, the more production. Also, it needs bigger budget, but less bad euro ratio. The more percentage of self-consumption means the return of investment is going to be lower because it's more expensive the energy consumed from the grid than the one given to the grid from the PV installation, if the national legislation allows it. In Spain, for instance, it's only allowed since 2019. If the national legislation doesn't allow that possibility, of course, any extra produced energy that is not self-consumed is going to generate nothing to the user. In this slide, you can see an example of the generation versus consumption in a building. In blue, you have the consumption of the dwelling, and in yellow, the solar generation. There are other considerations to take into account when doing the calculations. First, you have to know the solar irradiance of the locations. For that, we got a tool developed by the JRC from the European Union, that is the PVGs. There you can select the location, the technology, the mounting position, and the peak power. Here is an example of an installation in Murcia, in the southeast of Spain. You can see how you can select different options, and you got the radiation for that zone and the monthly energy output for a given PV installation. To calculate the final energy production, you have to take into account the performance losses. It depends on the position of the PV module. The slope, the optimal one depends on the location, and the use is different in summer and winter. And for instance, in Spain goes from 20 to 40 degrees. Also the azimuth, that in Europe the optimal one is 0 degrees south. Sometimes in roof installations it's better to install it on the roof without any additional structure, because the installation is cheaper and works better that way rather than with a more efficient one. Also, it's important to avoid shadows, and in bigger plants with different rows you have to keep the distance between them. Also, when selecting the inverter, you have to consider the parameters. The power capacity usually is slightly smaller than the module's capacity, and also it has limitation on voltage and current. For that, you have to select properly the connections in series and parallels between PV modules. Now we will finish with the current state of the PV energy. First, we will see the global annual production by region in 2020. As you can see, the production in Asia has gone from an 80% in 2010 up to a 92% in 2020. Of that, 67% of the production is made in China. The global cumulative PV installation by region in 2020. The total cumulative installation amounted to about 710 gigawatts at the end of the year 2020. These percentages are related to global installed PV capacity, including off-grid system. As you can see, the 36% of the total installations are in China. Then we have Europe with a 23%, with the biggest share in Germany, and North America is the following one with a 12%. The cumulative PV in Europe from 2000 to 2020, it is shown in this graphic. As you can see, the main production is in Germany, followed by Italy. If we see the solar per capita up to 2019, the first one is still in Germany, followed by Netherlands and Belgium. Thank you for your attention. If you have any doubt, you can contact me in my email.